Okay, I think it's a good idea to get into the habit of starting on time, so let's get started with today's colloquium. So this year we made actually a few changes with our colloquium. You might have noticed that we have new flyers and there is a new web page. And colloquium videos are going to be posted on the YouTube. And well, it's not a substitute for actually coming to colloquium, so I would still like to encourage you to come to the colloquium. So, so this series was officially called the Physics Research Conference until last year. And we have been using this term since 1922, since the time of Millikan. But, so we want to be respectful about our history, but this name caused a lot of confusion. So this year we decided to rename it officially as a Physics Colloquium. So this is the second physics colloquium in the entire history of Caltech. So just to remember, just to have institutional memory, the colloquium website describes the history of Physics Research Conference written by Judy Goodstein. So we have we also have a new tradition that we have tea and cookie after the colloquium rather than before. And so that way we'll have lots more talk about because we might have talk about colloquium that we would have just heard about, for example. And on a special occasion like today, we have wine and cheese in lieu of tea and cookie. Since there are people with family obligations, so it's important that the colloquium ends at 5 p.m. so people can go and pick up kids, etc. And so the colloquium host is responsible to keep time. So this brings me to one more change that we made. So traditionally, if a speaker is a Caltech member, there were no designated host and there was no introduction made. And there was some reason for this, but that causes some awkward moment that some of us remember. And so we decided that the chair of the colloquium committee or an appropriate substitute should introduce a Caltech speaker, and that's what I'm going to do now. So today's speaker is Dimitri Mawet. He is an associate professor of astronomy at Caltech. He did both his undergraduate and graduate study at the University of Liège in Belgium and came to JPL as a research scientist. He joined our faculty in 2015 and was made a senior research scientist in the same year. At Caltech, Dimitri founded Exoplanet Technology Lab, where he and his group are pioneering new techniques to detect and characterize exoplanet with Palomar and Keck telescope. Well, this week it's a particularly timely topic because of the Nobel Prize to the pioneer of this subject. The title of this colloquium is New Frontiers in Exoplanet Science in High Contrast Imaging and Spectroscopy. So please, Dimitri.
Thank you, Hiroshi. Good afternoon, everybody. I'm really thrilled to be presenting some results from my group and some of my research exploring new frontiers in exoplanet science with high contrast imaging and spectroscopy. So I would like to go back to two age-old questions. They've been around for millennia, but they map out into overarching scientific goals which I've articulated my talk around. First, characterize the diversity of planetary systems, understand the formation and evolution of those systems. 3, explore the properties of exoplanets to identify habitable worlds. And 4, search for biosignatures. So I would like to start with the founding moment, or moments, I should say, in our field, which some of us call the Second Copernican Revolution, which started with the discovery of exoplanets. I think the first one is fair to say can be attributed to Alexander Wolfson and Dale Frail, who discovered 2 exoplanets orbiting a pulsar. But perhaps most significantly, and as was recognized by the Nobel Prize Committee a few days ago, Michel Mayor and Didier Queloz were the first to discover planets orbiting other sun-like stars. And so that discovery was made using the radial velocity technique that I will briefly describe at an observatoire I'm very familiar with, which is the Observatoire de Haute-Provence in the south of France, with a very small telescope there. So since then, we've discovered more than 4,000 exoplanets, showing a mind-boggling variety of types. Most of these discoveries have been enabled by the radial velocity technique that Didier Queloz and Michel Mayer pioneered at this small observatory, and the transit technique, which literally exploded with the launch of the Kepler Space Telescope in 2009. You see, there are other techniques, and the last one of them is dear to my heart. This is high-contrast imaging and spectroscopy, which so far has been responsible for only 1% of all planets discovered. And I'd like to explain why that is the case. Direct imaging of exoplanets is extremely hard. The best analogy we've come up with over the 2 decades, I couldn't find a better one, is that of a firefly flying around a lighthouse seen from thousands of miles away. And so the luminosity of the firefly, or the planet, is composed of 2 terms, the reflected light term and the thermal emission. And so by measuring both reflected light and thermal emission from exoplanets, one can infer properties about their atmospheres. But before we can do that, one has to deal with a very interesting and daunting challenge, which is the star itself. The star is, of course, much more luminous than the planet, be it in the reflected light regime or the thermal emission regime. The extreme contrast ratios one has to deal with range from 10⁻⁴ for self-luminous gas giants to 10⁻⁸ for temperate Earth-sized planets orbiting late-type stars, all the way to 10⁻⁻⁻ for temperate Earth-sized planets orbiting sun-like stars. It would be okay if it wasn't for the tiny angular separation that these objects make on the sky. So 1 AU, 1 astronomical units at 10 parsecs is 0.1 arcsecond, which forces us to use the largest possible telescopes. So how do we proceed? What is the standard technique to image exoplanets? So we rely on a technique by French astronomer Bernard Liaud. Oh, sorry. So we invented coronography. Coronography is a technique that was developed in the 1930s to observe the solar corona outside of natural eclipses. And so Bernard Liaud was also an instrumentalist and understood diffraction. So he came up with an idea to use a focal plane mask that will block out the light from the sun, and downstream from the focal plane mask here at the focus of the instrument is a Liaud stop. So this is a diaphragm that, in conjunction with the focal plane mask, the field lens, is removing the effect of diffracted light. So it would be fantastic if we could use that concept as is. Unfortunately, wavefronts, as they propagate through our atmosphere and our instrument, pick up tiny imperfections on the optics and build up these aberrations that destroy the efficacy of a coronograph. So in order to deal with those aberrations, one now has to rely on adaptive optics, which is another technique essential to high-contrast imaging. Adaptive optics uses a deformable mirror that can change its shape very accurately and, if needed, very quickly, so as to correct for these optical aberrations, restoring the diffraction limit of our instrument. Then a coronograph can be used efficiently, extinguish the light from the central star, revealing faint off-axis planets. Not all coronagraphs are created equal. There are a dozen or so different coronograph types. I've been focusing on one coronograph in particular over the past 15 years, called the VORTEX coronograph, which relies on an optical singularity induced on the starlight itself. So the point spread function at the focus of our instrument is forced to have this phase screw dislocation, and for that we use a specific focal plane mask. And when the starlight sees this phase screw dislocation, this singularity in the electric field, it is forced to propagate outside the geometric pupil area of the system downstream, where it can be caught by the Liaud stop. A planet comes at an angle and hits the vortex plate off-axis and doesn't see the central singularity and then propagate normally. So we've created a perfect filter that will filter out the on-axis coherent signal and let anything off-axis go through. So in details, the physical action of a VORTEX coronograph is to multiply the point spread function. So you may recognize the textbook point spread function expression for a circular telescope, which is the Bessel function of the first kind divided by its argument. We multiply that function with a phase ramp e to the I L omega. Omega is the azimuthal coordinate in the focal plane. L is a parameter we call the topological charge. And then we take the Fourier transform using the concept of Fourier optics to go from the focal plane to the pupil plane. That expression is equivalent to the Hankel transform of the Bessel function of the first kind of order equal to the topological charge of the vortex and can be rewritten very simply by this expression here. So what I found during my PhD more than 15 years ago was that integral had known solutions. It's also called a Weber-Skafetlin integral, which is strictly zero for r, so the radius smaller than the telescope radius itself, as seen from the pupil plane downstream from the focal plane mask. That is strictly zero only when the topological charge is an even number. And so we've now created a filter that can remove the starlight and let off-axis planets go through perfectly. And perfectly means in the equations only. In reality, there are lots of imperfections that come into play that one has to deal with. The first one is to manufacture this coronagraph. And so it took many years to go from the paper concept to actual devices that we could use on various observatories. And so we've developed two main technologies. I will mostly focus on this technology that is based on sub-wavelength gratings imprinted into diamond substrate. And so these gratings have the property of modifying the properties of the electric field to induce this phase ramp. So we've manufactured a series of devices using nanotechnologies, and we've deployed these devices on various telescopes from Chile to Arizona, and in particular the Keck telescope in Hawaii. So we installed one of these devices in 2015 in NERC2, an infrared camera behind the adaptive optics system of the Keck telescope, in collaboration with Jean Serabin from JPL, Keith Matthews from CATEC, and a very large team of European collaborators. Out of this venture came out a few technical papers and a lot of the science results I will discuss about today. Now I'm going to go into the core of the matter, which is to try to address some of these overarching scientific goals. The first one being about demographics of exoplanets. You might have seen this diagram many times. This is the most recent one I could glean from the NextEye database. This is a mass versus semi-major axis plot, mass in Jupiter masses. All the dots in this diagram are exoplanets that have been found by all the techniques listed here. So you see a lot of points there very close to the star. It's short separations discovered by the transit technique and mostly the Kepler Space Telescope. You see a lot of blue dots from the radial velocity technique, which as time goes by extends to longer and longer periods, so larger and larger semi-major axis. And then in the upper right corner of this diagram, you see all the directly imaged planets so far. So that's roughly 1% of all planets discovered so far. You see in this diagram the various biases that all of these techniques have. So transit confined to short periods, radial velocity as well, but now extending further out, and direct imaging mostly limited to the upper right corner, so in the regime of gas giants at large separations. So what we've learned, and mostly from the Kepler mission, is the relative paucity of gas giant planets. This is a histogram of planet types in terms of their size. And so you see that the frequency of gas giants is fairly low. On the other hand, the frequency of small planets is unexpectedly large. And in particular, two types of planets have been discovered by Kepler which do not exist in our solar system. And this can be seen in this amazing result from B.J. Fulton, Andrew Howard, and their team, which is deemed the photo-evaporation gap, or the Fulton gap, which separates the super-Earth and the mini-Neptunes, and it is thought to be driven by photo-evaporation processes. Perhaps the next frontier is to try to learn more about these objects, because all we have so far are size and mass measurements, which are the two quantities that can be measured respectively by transit and radial velocities. However, when we can do these measurements of both the radius and the mass of the planet, then we can infer their bulk composition, which is something that transit and radial velocities have done wonderfully well and made plots like this one showing the planet radius as a function of planet mass, which can then be compared to models of planet interiors. You see on the right the gas giants, consistent with models of pure hydrogen and helium envelopes. The ice giants in the middle showing a great variety of planet compositions from rocks to hydrogen and helium envelopes. And then on the left side of this plot, you see the terrestrial planets, mostly consistent with pure rock, just like the Earth. Something that transits and radial velocity techniques, these powerhouse techniques, haven't really been able to do is to retrace the formation history of this planetary system for good reasons. They both rely on measurements of the star, and young stars are very active introducing noise into the measurements. And perhaps this is a realm where direct imaging and direct detection techniques can really shed some light onto, so to speak. Which leads me to the second part of this talk, which is to understand the formation and evolution of planetary systems. I like to divide the formation process into three different phases. The protoplanetary disk phase from 0.1 to 1 megayear, the transition disk phase from 1 to 10 megayear, those are rough numbers, and then the debris disk phase from 10 to 100 megayear plus. So let's start with the protoplanetary disk phase. This is here an animation artistic rendition based on numerical simulations that were done in the early 2000s. So you see rings and gaps, mostly. Well, ALMA, which was truly a revolution in the submillimeter domain, using this large interferometer in Chile, has revealed an amazing gallery of such protoplanetary disks, showing these textbook rings and gaps, and other substructures such as spirals or asymmetries. And so these are real images. Those are not simulations, and are truly mind-boggling. So ALMA is sensitive to millimeter-sized grains. And so it can trace grains really well. It can also measure gas and gas velocities. However, ALMA is not very sensitive to small forming planets. And the leading theory for the creation of these gaps is the formation of gas giant planets. So what is the best way to look for these planets? Well, I would argue that the best way to do that is to use direct imaging techniques in the wavelength range going from 1 micron to 5 micron, so covering the J, H, K, L, and M band. So those are atmospheric windows through which we can see. And so indeed, direct imaging is best done at those wavelengths. In particular, I've been focusing on the L and M band, which are between 3 and 5 microns. And for good reasons, if you look at these model of planet spectra or spectral energy distributions, you see that they mostly peak in those wavelength ranges. And so for a vast range of temperatures, all the way down from 130 Kelvin for Jupiter to 1600 Kelvin, which is the temperature of Beta Pictoris b, a directly imaged planet. So what direct imaging can do is not only detect those planets, but take spectra and constrain those formation models and initial conditions. So there are a range of model families with warm and cold start hypotheses that lead to different predictions for the luminosity of planets. So if we observe a large enough sample of planets, one can then inform directly the formation processes. Going a little bit into details here, there's an emerging family of models that we use today, which are of accreting protoplanets, using circumplanetary disk models to predict the infrared luminosities of these objects. So the important takeaway message from this model plot here from collaborators Zhu from University of Las Vegas is the fact that they also peak. These curves peak in the thermal infrared around 3 to 5 micron, and are actually more luminous than a planet without accretion. And so the thermal infrared regime, in a nutshell, is really where we want to look to detect and characterize these forming planets. So this is here the poster child protoplanetary disk system, which recently showcased these two protoplanet discoveries. So PDS-70b and PDS-70c. Those planets were discovered by a facility in Chile, where I used to work, called the SPHERE instrument at a very large telescope. recently, MUSE, an optical integral field spectrograph, detected the H-alpha emission from these two protoplanets. So we looked at this system with the L-band VORTEX coronagraph at the Keck Observatory and redetected both PDS-70b and perhaps PDS-70c. So the detection for PDS-70b is non-contentious. It's pretty well acknowledged now as a bona fide protoplanet. For PDS-70c, there is a bit of controversy because you see it's very close to the disk ring, and it can be mistaken for disk structures. So there is still more work to be done to understand the nature of this hotspot at the location of the putative PDS-70c candidate planet. And so, but for PDS-70b, with our L-band photometry data point, Jason Wang, one of my postdocs, recently inferred the temperature of the planet to be between 1,000 to 1,300 Kelvin, with a radius between 2 and 4 Jupiter masses. So truly a young planet in the process of building up. We also looked at a prototypical disk system, protoplanetary disk system, TW HYDRA. This one is very interesting because it's close. It's close to us. It's only 60 parsecs away, which is on average twice as close as the ALMA images I showed before. And so we looked at this system again with the same coronagraph at Keck Observatory. And we looked in particular at the location of the gaps in the disk revealed by ALMA. You see this image in the upper right corner from ALMA showing clear gaps. And so within the gaps, we were able not to detect the planets. Unfortunately, they might be too light to be seen, but we could put upper limits around 1 Jupiter mass for the gap number 2 to 4 and 2 Jupiter masses for the gap number 1. So these plots that I will use a lot in my talk are in Jupiter mass units and projected separation in astronomical units here. And there are upper limits, so everything above the curve can be detected, everything below cannot be detected. So what we could do with this data set too is to constrain the mass accretion rate on these planets using the circumplanetary disk models from collaborator Zhao and Zhu. And so now we are in a position to actually see these planets eventually for PDS-70, or at least constrain their masses and mass accretion rates, so really informing these formation models. Moving on in time now to the transition disk phase. So now these disks are in the process of clearing out material from the inside out due to both the activity of the star and also accretion onto forming planets. And so transition disks are active places of planet formation. So we looked at one of these famous transition disks called HD 141569. This is a beautiful image on the right from the Hubble Space Telescope and ACS camera, showing again these substructures and now in reflected light. So this is due to the scattering from the starlight coming from the center. But you see that the ACS camera is an inner working angle, so an ability to image planets that is limited to about 1 arcsecond or so. Everything within the darkened region here is basically saturated, and so we cannot see anything within that region. So with a 10-meter telescope, that is the Keck telescope, and our VORTEX coronagraph, we could go almost all the way down to the diffraction limit and uncovered a new ring system that extends from about 30 to 70 AU. So together with Hubble Fellow, former Hubble Fellow from Caltech, Elodie Choquet, we took our data, our images, and did an extensive radiative transfer modeling along with the spectral energy distribution data points from far infrared facilities such as Spitzer, Herschel, WISE, and the others. And to infer the temperature of this ring to be around 100 Kelvin, we could also infer the composition. We know now that the inner ring is made of pebble-sized grains and composed mostly of olivine, so silicates. So we found that the system is indeed still actively agglomerating building blocks of planetary embryos. Moving now further in time in the debris disk phase, from about 10 to a few hundred mega-years up to a giga-year, this phase is crucial for small planets. This corresponds to the late heavy bombardment in our solar system, which is thought to be responsible for delivering volatile elements from the outer solar system inside the rocky planet realm. And so I'm very much interested in that phase because we know of many debris disk systems, and there might be signposts for giant planets that we then image and characterize. Why are those disks considered as signposts? Perhaps because the leading theory for maintaining these rings of dust is the gravitational perturbation due to giant planets exciting the eccentricities of planetesimals, sending them into a collisional cascade. So a question we tried to answer formally a few years ago, are debris disks signposts for these long giant planets? This was further motivated by the fact that a lot of these directly imaged planets, this is here a family portrait of some of them, the most famous ones, but the majority of them here on the right side are in system with dusts. And so, but we never really showed that it was true. Moreover, we discovered a few years ago with a former Caltech grad student, Trevor David and Mike Bottom, a companion to another dusty star, HR 3589. And this time it is not truly a giant planet, but this is a more massive object orbiting outside the debris disk belt. And so the canonical picture for debris disk is that of giant planet orbiting within the ring, and so exciting the eccentricities of planetesimals. But for this particular system, we found a more massive object orbiting outside the debris disk belt. And so a paper a year after our discovery showed that you could indeed shepherd and excite this collisional cascade through causae lead-off interactions. So this is showing you the intimate relationship between these disks and planets and leading to dynamical instabilities that can really affect the inner systems. So we set out to perform the most comprehensive direct imaging survey for giant exoplanets in dusty systems, along with JPL postdoc at the time, Tiffany Meshkat, now at IPAC, and former Caltech grad student, Marla Bryan. We assembled a large sample, 130 debris disk stars, for which we collected data from both the Keck telescope and the VLT telescope in Chile. We also assembled, with collaborator Brendan Border, a sample of 300 control stars, which are dust-free. Just to make sure that these systems belong to the right sample, we looked at the WISE All-Sky catalog. WISE is an infrared space mission. And so we ensured that our samples were contaminant-free. Fast forwarding a few years, that's how long it took to continue the survey and perform the statistical analysis. We found indeed that there is an occurrence rate correlation between giant planets and debris disks. And we found that debris disks are 10 times more likely than dust-free systems to host gas giant planets. Perhaps in summary, showing the universality of interactions between these giant planets and debris disks, which is responsible for igniting these large-scale dynamical instabilities. Accessorily, we also found an underlying correlation with the metallicity of the system. And finally, we found that dusty systems are perhaps the most promising targets for direct imaging searches because our chances of seeing one is 10 times more than in dust-free systems. And so, with that result, we started yet another survey, this time going really as deep as we could with current facilities. And so now this is an informed survey. So we look at objects that are confirmed to have dust, and then we go very deep as we can. So our first target in that survey was Epsilon Eridani. This is a very famous debris disk, the poster child of all debris disks, perhaps, because it's surrounded by a prominent and very complex debris disk. It's one of the Fab 4. So it is also a very interesting target because 15 years ago or more, the radial velocity technique discovered a putative 1 Jupiter mass planet orbiting at around 3 AU in that system. The problem and the conundrum and the interest in looking at this system is that the eccentricity as measured by the radial velocity technique was around 0.7 or so, which would make the planet cross the inner ring, which is not really plausible. So there was definitely a problem there. So we asked the question, can we image and characterize that planet today with current facilities? You have to remember the challenge here is that this planet is the lightest one potentially ever imaged. So we looked at this system with our VORTEX chronograph at the Keck telescope. This is the signal-to-noise ratio map after our first pass on the data. So you see a lot of hotspots there. Those hotspots are really the bane of high contrast imaging. We call them speckles. They are the result of imperfect correction of the wavefronts by the adaptive optic system, and so they can masquerade as potential planets. So one has to be very careful about dealing with these systematics. We spent 3 half nights of telescope gathering 5 hours of open shadow time data on this subject. So now I'm comparing the sensitivity of our measurement in terms of mass versus projected separation. So the axis is going from 1 Jupiter mass to 10 Jupiter mass and 1 AU to 5 AU. So we are probing the system on solar system scales. So the top map here, this completeness map with blue being 0% complete, and red being 100% complete. This map was the best previous data set on this subject. The result on the bottom here is our data, is our Keck data. So this is blowing the best previous results completely out of the water. So we got results, sensitivity that goes all the way down or almost to 1 Jupiter mass at 3 AU. So I really asked the question, is there really a planet in that system? So I worked with my colleague Andrew Howard, Leah Hirsch, who was finishing her PhD at Berkeley, and other collaborators here at Caltech to perform a joint Bayesian analysis, putting together our upper limits from the direct imaging campaign together with 30 years of RV data. This is a beautiful data set going back all the way to 1987, and has been reprocessed by state-of-the-art RV pipelines from B.J. Fulton, Andrew and his team. And so together with the direct imaging data, we re-derived new parameters for the planet. So the mass of the planet is about 0.8 Jupiter mass, so slightly lower than initially thought. The orbit is still around 7.4 years, 3.5 AU. But now the eccentricity of this new solution is consistent with a circular orbit, which fits much nicer with the debris disk system. So which leads me into the third section of this talk, which is about exploring the properties of exoplanets to identify potentially habitable environments. So I'm now forward-looking. So how can we do that? So atmospheres of exoplanets are really the window into all of their properties except mass, radius, and orbit. And so the study of exoplanet atmospheres requires spectroscopy. So spectroscopy of exoplanets can be done in 2 different ways. So one can use a transit technique, and so by chance, if the orbital plane is aligned with our line of sight and the planet passes in front of the star and some of the starlight filters through the atmosphere, one can take a measurement. And then this is here something that's been done already, and this is a compilation of hot Jupiter spectra taken by David Singh, compiled by David Singh. And you see at the top here, clear atmospheres showing very prominent water absorption lines, alkali lines, and as we go down in this family portrait, we go into the realm of planets that are hazy and cloudy, which are now muting all these spectral features. And it seems that for transit spectroscopy, at least, the prevalence of cloud that has been found in transiting planet is really a break into and then a veil onto the properties of their atmospheres. That is also partially the case, at least for directly imaged planets. This is here a family portrait of spectra taken for directly imaged planets. You recognize features of water, methane, carbon dioxide. But again, these spectra are very much affected by the presence of clouds in exoplanets. So please ask me about clouds after I'm done. Anyway, so these spectra are taken at very low spectral resolution, typically 100 to 1,000. Now, something that I found really interesting a few years ago is that when we go to higher spectral resolution, so now going the few thousands to a few 100,000 or so, these molecular bands that were detected in those spectra split into hundreds, if not thousands, of lines. And so there's a lot of information to be recovered from those lines. And it's something that Quinn Konopaki, one of my collaborators, explored in 2013. I think this is a seminal paper from Quinn. So she took a spectrum with OSIRIS at Keck of HR799c. This is the data in red here, the model in black. And then she cross-correlated the data, almost the raw spectrum. There was a bit of processing done, but she cross-correlated the spectrum with templates of molecules that can be either measured in the lab or calculated. And so she did that for carbon monoxide, she did that for water and methane. And then she looked at the cross-correlation function between the data and those models and found 2 peaks for both water and carbon monoxide, no peak for methane. So this technique is very powerful. It's now called molecule mapping. We've applied it with my former postdoc, Ji Wang, on HR799C again, now at very high resolution, and also confirm the presence of water. So we can use these high-resolution spectra now to directly map the molecular content of these exoplanets. Moreover, what we can do at very high spectral resolution, now maybe 100,000 or so, is to measure the planet spin. So this is a result from Ignace Selen obtained at CRIRES, with CRIRES at the VAT, a very high-resolution infrared spectrograph. This is a position versus velocity diagram showing Beta Pictoris b, one of the very few directly imaged planets. If you look at the crosscut here in velocity and the plot on the right, you see that the peak, the line profile is broadened compared to the instrumental line profile in dashed line. And so this broadening is due to the rotation of the planet itself, and so measuring the width of this line profile then is a measure of the planet spin or length of day. Moreover, the shift of the peak to the systemic velocity is also a direct measure of the planet RV, to be distinguished from the stellar RV. Now we directly measure the planet velocity along its orbit. Something we can do with high-resolution spectroscopy is from a time series, now in the time domain, a time series of these line profiles, we can then invert them into maps. Something that's been done on Born dwarfs by Ian Crossfield. This is here an animation showing Luman 16b and its cloud map. And something we attempted to do with Ji Wang, my former postdoc, using Keck NeurSpec data a few years ago. What high-resolution spectroscopy can also do is to sidestep this speckle noise issue. So I showed you this SNR map, which is truly the bane in high-contrast imaging. We've been fighting this problem for years. At high spectral resolution, now you're interested in all these individual molecular lines, and those are not affected by the speckle noise at all. So we completely sidestep the problem by going to high spectral resolution. And so in the lab, we've worked hard over the past few years to develop technologies to exploit this property of high-resolution spectroscopy for directly imaged technologies. So now we aim to combine adaptive optics, coronography, and high-resolution spectroscopy. And we found that using optical fibers is actually adding an extra layer of filtering now that we can truly clean up the planet signal and send it to the high-resolution spectrograph. So the experiments in the lab worked great. The simulation from my former postdoc, Ji Wang, were truly mind-blowing. And so we decided to build an instrument to test that on sky. So that instrument is called the Keck Planet Imager and Characterizer. This is a collaboration between JPL, University of Hawaii, University of California, Los Angeles, Super-Woo Telescope, the Keck Telescope, and funded by the Heising-Simons Foundation and the NSF. So KPIC, in short, is a series of upgrades to the Keck Adaptive Optics System and Instrument Suite. We installed a new wavefront sensor for the Adaptive Optics System. We installed new VORTEX chronographs recently. And perhaps more importantly, we installed a fiber injection unit that will place this single-mode fiber at the location of a directly imaged planet and propagate its light to the existing infrared spectrograph NeurSpec. And so we can collect these high-quality, information-rich spectra on these directly imaged planets and do all the things I showed before. So this week is very exciting for the project. Tonight we have an engineering night to get the system online. And this weekend we have about 3 nights exactly of science to do the first demonstration of this technique on sky. I'd like to acknowledge the work of my team. So Jacques Delorme, who's actually coming from Hawaii to help us with the run today, and Charlotte Bond, who was taking care of the pyramid wavefront sensor, and Jackie Pesato, who is starting a PhD on this project, and many other students involved in the project. So what I realized when getting into this high-resolution business is that there is truly a confluence in exoplanet science with infrared high-resolution spectroscopy. So this is such a powerful technique. I mean, looking back at the history of astronomy, high-resolution spectroscopy was transformational for stellar astrophysics. I think we are about to witness the same revolution in exoplanet science. High-resolution infrared spectroscopy is something that transit spectroscopy needs. That's something that direct spectroscopy of directly exoplanets can tremendously benefit from, and it also enables radial velocity measurements in the infrared, complementing the optical facilities. And so for that reason, with JPL and collaborators from the Museum of Natural History in New York, we built a pathfinder instrument called PARV, the Palomar Advanced Radial Velocity Instrument, which was built here at Caltech. And it actually was built from the ground up to be behind an adaptive optics system, so benefiting from some of these technologies. And so when the telescope and adaptive optics system provide a diffraction-limited beam at the theoretical diffraction limit, whose size is set by this fundamental limit, then the size of the instrument is completely decoupled from the telescope itself, contrary to seeing limited instrument which scale in volume as d to the third power. And so now we've built an instrument that is extremely compact, the size of a big laptop, that can be efficiently stabilized in temperature. And so this instrument saw its first light last June, and this is actually our pathfinder to a similar project we are now proposing for the Keck telescope called HiSpec. So HiSpec will be an almost exact copy of PARV, extending the wavelength range to the Y band and K band, so from 0.95 to 2.45 microns. We're going to explore new technologies such as photonics lantern, which are super single-mode optical fibers, which fan out into multiple fibers. So this is very exciting technologies. Something that these two instruments will benefit from is the laser frequency comb technology, which is developed here at Caltech as well, as an absolute ruler that is essential to do these Doppler measurements. I'm entering the last part of my talk, which is truly forward-looking now, and is about the search for biosignatures. So one ultimate goal of exoplanet science, and in particular direct imaging and spectroscopy, is to gather images and, more importantly, spectra of faint pale blue dots. So this is an image of the Earth taken by Voyager 1 in 1990, and this is here a spectrum of the Earth covering the optical and infrared regime. In the spectrum of the Earth, you recognize signatures of oxygen, water vapor, carbon dioxide, and methane. You also see the vegetation jump here in the red. This is a low-resolution spectrum of the Earth. The combination of these biosignatures is what we call the signs of life. So that's something that we are looking for on planets orbiting other stars. If you look now, again, I'm hammering this down, but if you look at this Earth spectrum at high resolution, which is something we did with my former postdoc, Ji Wang, this spectrum in the near infrared is very information-rich. It's got thousands of lines, and now we split it into its constituents, and you see the richness of the spectrum in the 1 to 2.5 micron range, even all the way to 4 microns. Okay. Before we can get those spectra and do all the cool things I mentioned, such as measure spins and measure molecular abundances or so, one has to work really, really hard. This is a plot I made for the National Academies of Science. I was in the Exoplanet Science Strategy Committee last year. And so this is a plot showing contrast versus angular separation. All the dots in this plot are generated from occurrence rate that have been extrapolated from the Kepler measurement from short period planets, so take it with a grain of salt. So the red dots are gas giants. The yellows and oranges are Neptunes and mini-Neptunes. And all the green dots are Earth-sized planets, with the highlighted dots being Earth-like planets in the habitable zone of their star. So in the upper right corner, you see what we call contrast curves. I've shown 1 or 2 before, and they show the limits of our instruments. Everything above the contrast curve can be detected. Everything below cannot be detected. So you see where we are today, typically 10⁻⁶ at 0.5 arcsecond. To access this huge reservoir of planets to see and characterize in details, we have to literally make a quantum leap in performance. that will be brought by the next generation of ground-based and space-based telescopes, which will have sizes about 3 to 5 times larger than current generation telescopes. So in principle, if we apply the same techniques we use today, these curves will slide by a factor 3 to the left, right? But we still have to work hard to bring our limits down into these regimes. And so that will be done by a combination of improving our adaptive optics systems. Coronagraphs are the best they can be. They just suppress diffraction. Maybe the most difficult problem in that regime is the adaptive optics system, so those wavefront corrections and the speckles I mentioned before. So we can use adaptive optics, improve it, trying to push it to its limits. We believe the limits for adaptive optics for ground-based telescopes are around 10⁻⁸ or so, which is great because given the size of the future telescopes, such as the 30-meter telescope, we should be able to access some of these green dots over here. So these green dots, the circles, are for planets around M-type stars, while the squares are for planets around Sun-like stars. So you see that giant segmented mirror telescopes will be able to access these dots if we work really hard. Okay? So now I would like to show you this plot, draw your attention to this line here, which is the requirement for future space missions. So in space, the telescope size is obviously smaller. But then the instrument, the observatory itself, is much more stable, and so we can address these wavefront errors much more precisely, plus we don't have to deal our Earth atmosphere. So one of the recommendations of the panel I was on last year was that NSF should invest in both the GMT and TMT and their exoplanet instrumentation. So to answer that call, with colleagues, I proposed a new instrument for the 30-meter telescope called MODIS, for multi-object diffraction-limited high-resolution infrared spectrograph, which is a direct extension of the PAR-V high-spec line. So this is based on the same model that we are proof testing today at Palomar Telescope and tomorrow at Keck. And so, believe it or not, this instrument, to my greatest surprise, was selected as the first light instrument for the 30-meter telescope. So it's the first wave of instruments for the 30 telescope. So now we're working with TMT to design this instrument. The second recommendation of our committee was that NASA should lead a strategic direct imaging mission capable of measuring the reflected light spectra of temperate terrestrial planets orbiting Sun-like stars. And so NASA has ordered 2 concept studies, one led by JPL called the Habitable Exoplanet Observatory, which I was a part of, and LUVOIR, led by the Goddard Space Flight Center. So these are really forward-looking mission concepts, flagship mission concepts for NASA. They don't just do exoplanet science, they do a lot of other science, but they are designed with exoplanet imaging in mind. So it is surprising, maybe not so surprising to me, that both observatories have elected the VORTEX coronagraph as their core technology to be flown on these future missions, potentially. So recognizing the strategic importance of technology developments, a few years ago when I arrived at Caltech, I invested almost all of my startup money into a lab. So the lab is called the Exoplanet Technology Lab. It is made of several test beds that are really state-of-the-art. And so now it's self-supported by a series of grants from NASA, the Exoplanet Exploration Program and JPL R&TD program. So in that lab, we refine the technologies to be used on these future concepts, future missions, and future instruments. In particular, the VORTEX chronograph, which is the baseline for both HABEX and LUVOIR. We also refine the high dispersion coronographic technique, now going to these very high spectral resolutions and trying to optimally combine these high-resolution spectrographs with coronagraph and wavefront control techniques. And then we come up with crazy new ID. The latest one I'm really excited about is called the VORTEX Fibranular. And Dan Echeverry is in the room, is my grad student working on that very hard. So we got our first result in the lab. So what this technique will allow us to do is to detect, but directly characterize planets at or within the theoretical diffraction limit. So if you have more questions about that, I'm sure Dan would be happy to answer. Anyway, this is my last slide. This is the arc of my research, starting from technology developments, new technologies in the lab, pushing the limits of instrumentation, proof testing those techniques on our cherished telescopes, such as the Palomar telescope and the Keck telescope, while doing science at the same time. I think it's when we push the technologies to their limits, I think it's important to do that while doing science, and we do a lot of science. And then that is in preparation for future instruments and surveys on these very large ground-based and space-based telescopes, such as the 30-meter telescope, which is extremely important for us, as well as future flagship missions such as HABEX and LUVOIR. I'd like to end this talk by acknowledging my students, the top row, all the postdocs that have gone through my group. The current active postdocs are here. People are still around and working with us. Nem is at Caltech Optical Observatories. He's really instrumental into making all these things a reality. And then the alumni from my group here, some of them have got faculty jobs very recently. And then all the SURF students that we hosted over the summer, the past 4 summers. This has all been a blast, and I thank you.
Thank you very much for the very exciting colloquium. And I asked him, Dimitri, to end well before 5 o'clock, so we have some time for questions, and I appreciate that too. I'm sure there are lots of questions, so please. Okay?
So you're looking at these molecular lines. These molecules are also present in the Earth's atmosphere, so how do you make sure you're not seeing them from the Earth?
Good, very good question. So the main factor we rely on is the systemic velocity of the star and the orbital velocity of the planet. And so in velocity space, these lines are shifted by tens of kilometers per second.
So this doesn't work if the plane is kind of perpendicular where there's no...
But the star, it's always as the star itself, the system itself always has a non-zero velocity. So there will always be a shift.
Okay. Any other question?
What is the farthest planet we have found, have observed? What is the farthest planet we have observed?
I think the Kepler field was several kiloparsecs away. Yeah, the microlensing planets, yes. Okay. But those are indirect detections. So the directly imaged planets, the closest ones we've seen, are around 140 parsecs or so.
Yes.
This may be thinking very far in advance, but when you're looking for biosignatures, I remember reading at one point there was this idea that life could only arise in a planet with a rocky inner planet like the Earth in the habitable zone and a gas giant like Jupiter in the outer areas, which serves to soak up comets or asteroids that might lead to extinction events. Would you restrict your attention to these kind of things, or would you just...
No, not really. The target list is already so small for us that it wouldn't make sense to restrict it further. So just to give you an idea, the target list for these future flagship missions is just maybe a few hundred targets at best. And so, of course, there are systems we don't want to look at because there are binaries, and our techniques don't work on binaries and things like that. So there are technical reasons for selecting the targets, but we want to be agnostic, relatively agnostic in our search for life.
But with enough data, you might confirm or reject that.
Yes.
Okay. Other questions? Yes, in the back.
So Dimitri, I know for opportunities, the spectral type of the star can potentially help you. For direct imaging, are you looking at certain types for various reasons?
So that's a good question. I think we are not so sensitive to the spectral type of the star as much as we are sensitive to the brightness of the star. So looking for bright stars always, because they provide the photons that allow us to do adaptive optics. So, but as long as the star is youngish and not too young, so that it's not obscure, so it provides the photons we need for the wavefront sensor, it's okay for direct imaging.
Yes.
Following up on Jesse's question, so if the star is cool enough, it's going to contain the speckles, and the star is going to contain lines from CO and water as well, right? So would that limit our ability in this molecular mapping technique to distinguish the planet?
So again, in that situation, we would rely on the orbital motion of the planet, and so the velocity shift of the planet to disentangle between lines from the star and that of the planet. But the thing we are trying to do with the instrument we developed is to remove all unwanted starlight from the spectrum, right? But there's always going to be some leftover in there, but then we can rely on velocity shifts between the star's light and lines and the planet line to further disentangle between the two signals.
Okay.
And does polarization play a role in characterization?
Yeah, so polarization has always been considered, at least in the US, I don't know why, maybe it's historical as a nuisance for direct imaging. But in Europe, I'm in between. I think it's both a nuisance and a blessing because there is a lot of information that can be extracted from polarization measurements. And so, as a matter of fact, we build an instrument at Palomar Observatory to do spectropolarimetry of born dwarfs. I couldn't talk about it today, I didn't have the time to, but this is something we are looking into. What information can we extract from measuring the polarization coming from some of these objects?
Fiona, you raise a hand.
Yeah, so what is the relative advantage and disadvantage of coronagraphs versus star shades?
Ah.
I know you're
So coronagraphs are, for these space missions, HABEX as a star shade as part of the baseline, and a coronagraph, so both. And we found that there is a very nice complementarity between the two technologies, at least that's the story. I think it makes sense because the coronagraph itself is internal optics to the telescope, and it's very nimble. So you can point the telescope, observe an object, point to another one, and you can go really fast. Now, the star shade is, I don't know how many thousands of kilometers away, so I think it's 50,000 or more from the telescope. And so when you have to repoint the star shade to a different target, it takes weeks to slew this spacecraft across space to repoint. And so it's not very nimble. So the number of objects that you can target with a star shade is limited by the fuel you can put on board that spacecraft. So what we designed for HABEX is that the coronagraph, internal coronagraph, would do the searches and orbit characterizations which require frequent slews and look at different targets. While the star shade, which is very high throughput because it doesn't rely on all these internal complicated optics, can be used to take these very deep spectra over a very large bandwidth. So we found that the two technologies were pretty complementary. But if you ask me if I can only choose one, I would take the internal coronagraph.
Okay. Did you raise your hand?
Yeah, I had a question. When you were describing going back, now I've forgotten the planet name, but going back to the data after your work with Andrew on characterizing its orbit, it wasn't quite clear when you described going back. Was it that this was simply something that you had dismissed as a speckle earlier, or was it that the sort of priors, should I think of it as the priors that you got from?
Yeah. So the image processing technique we use is very much dependent on the location in the image. So you can we use principal component analysis to reconstruct a model of the PSF. And we can do it for the entire image at once, but it's going to do an okay job. But if you focus the PC on one patch or an annulus in the image, it's going to do a much better job at reconstructing the point spread function. So our standard procedure is to reconstruct the PSF for the entire field of view available to us because we don't know where the planets are. But when you have a good prior on the location of the planet, you can really focus the post-processing in that part of the image that you're interested in. That's what I did, and that's when I saw there was indeed a point source, which could be in my SNR map. I haven't even checked. I don't care because I know that my PSF model is much better in this annulus. So the biggest frustration in direct imaging is that we know that we are not photon noise limited. We are limited by these speckles. And so photons from planets have landed on our detectors for about 2 decades. We are not just smart enough to sift through the systematics and see, disentangle between these speckles and our direct image planets. So this is a very active area of research, so in image processing, trying to use machine learning techniques and so forth. But that's why I went back to the data, because I was frustrated I couldn't see the planet while my detection map told me, you're very close. And so it was too close for comfort. So I went back and looked at it, and I saw something. So now it might still be a speckle, but we'll know the answer in 2 weeks from now.
I'm sure there are more questions, but it's about 5, so we should thank him. And also, we're going to have the wine and cheese at the patio, and so that way we may be able to extract more answers to them. So thank you.